So that is called decomposing them. Decomposing means to break down. It says it's a useful technique in calculus. You'll be using this in integration and differentiation. So when you do integration by parts, you're going to need like the pieces of the fraction in order to integrate or differentiate. And those are the two big concepts of calc. So you learn this now so that hopefully next year, when you see it, you'll kind of remember the process a little quicker than it being taught in calculus and then you using it directly in calculus as well, because it really is a pre-calc concept. But you're going to use the technique in calculus. So the fraction that's given to you, just as an example, we're going to work through this to decompose it in a little bit. This line here, I don't know what that is, but that should be there. But you can see that the x plus 7 over x squared minus x minus 6. That would be our simplified fraction. Everything that's simplified is considered one term. Our goal is to decompose it or break it down, and we're going to be finding these separate fractions. So that's what we're going to be doing. You're going to be given this piece, and we're going to be separating it, breaking it apart, figuring out what numbers go on top. So there's an x plus 7 on top when you simplify it, but when you break it apart, somehow you get a 2 and a negative 1. And that's our goal. We're going to figure out how can we get that 2 and negative 1 on the top, even though there's an x plus 7 on the left. So decomposing will be breaking fractions apart, separating them into a couple of pieces. So there are a couple of steps that are underneath, and these are actually not problems per se, but just kind of guidelines for us to follow so that when you look at a fraction, we need to kind of match the type of fraction it is, and then that's kind of the approach that we will take. But it says the rules and steps for partial fraction decomposition. So the first step that we'll have to ask ourselves for every problem is it an improper fraction? An improper fraction happens when the numerator power is bigger than the denominator power. And that's what this is talking about right here. So the degree of the numerator is greater than or equal to the degree of the denominator. That's called an improper fraction. So if it's an improper fraction, it says that we need to divide to make it a proper fraction. And we're going to divide using long division. So long division was something that we worked with way back in chapter 2. I'm pretty sure I said in chapter 2 we'll be using it again. And we'll use it again. So we're going to divide using long division. And I don't want to write long twice. There we go. Long division. So it says if it's improper, divide the numerator into the denominator, the denominator into the numerator to obtain a new fraction. And I know it looks weird, the notation looks weird, but the fraction that we'll have is the quotient, so that's whatever is on top of our division bar, plus then the remainder is going to be that leftover piece. And that'll then create a proper fraction for us. The remainder is what we'll be using for the proper fraction. So just to kind of give you an example so that you know what to look for, if I had something like x cubed over x squared minus 1, that's an improper fraction. The power on the top is bigger than the power on the bottom. So we would end up dividing that to try and get a proper fraction. Anything with a power that is larger on the top than on the bottom is considered an improper fraction. So you can come up with multiple examples. If it was equal to, it's also considered an improper fraction. So that will always be the first thing. So like with factoring, the first thing you're supposed to ask yourself is what is the GCF? With these partial fractions, we're going to say, is it a proper fraction? And if we say yes, then we can kind of move on from there. The other three pieces underneath are talking specifically about factoring. So it says factor the denominator. So that's really the first step, and we're actually going to do some math. So yes, we're going to say, is it proper or improper? But then the second step would be to factor the denominator. Completely factor the denominator into linear factors of the form px plus q. So that's like mx plus b. Raised to a power, and or reducible quadratic factors of the form ax squared plus bx plus c. So essentially, you need to take the denominator and factor it as far as it can go over the real numbers. We won't factor it into imaginary numbers, but it can be factored into real numbers. So a couple examples of linear factors. So if I had an x plus 1 times an x plus 2, that would be factored and it's linear. Whatever's in the parentheses is considered linear. So as long as the quantity in parentheses is linear, then it's considered a linear factor. We could also have x minus 2 quantity squared. Even though the quantity squared, the factor part is the part in the parentheses, and that's also considered linear. So yes, when you FOIL it, it's no longer linear, but factored form, whatever's factored is linear. The other one that could also be linear is x squared. And that's going to be the hardest one for you to think about, because for so much time you've thought about that as a quadratic. Why is x squared linear? What is really, when you say x squared, what does that really mean? Sean?
X times x.
Yeah, so if you write it kind of as like a factored form, that's really x times x. Both of those pieces factored are linear. So even though you're thinking, yeah, but it's x squared, well, x squared is really saying that you have the x as the factor, the squared part is just the power. So there's a difference between a factor and a power, and that's kind of what we need to think about in these problems. Examples of quadratic factors could be like x squared plus 4. Can you factor x squared plus 4? No, why not, Emerson? It's impossible to factor it because it's not a subtraction sign, it's a sum. We would have imaginary numbers. So this cannot be factored any further. It's quadratic, so therefore it's a quadratic factor. So the power is quadratic. We could have x squared plus 2x plus 4, and maybe that's squared. So this piece in the middle still cannot be factored any further. As long as it can't factor any further, then it's considered prime, but that's an x squared power. So it could have an exponent outside, that doesn't make it anything larger. It's just when it's in factored form, what does it look like? Questions? So the first step is going to be factoring it as far as you can break that problem down. So it needs to be completely factored. And then we're going to determine, once it's completely factored, what type of factors do we have? Are they linear factors or are they quadratic factors? So the third and the fourth steps are really kind of options that we're going to be looking at. Okay. So the third step says that we have linear factor decomposition. For each of the linear factors of the form px plus q, possibly to some kind of power, the partial fraction decomposition must include the following sum of factors. So after you have it factored, we're going to be trying to break up the fraction. And I'm just going to give us an example here. So we've got Alright, so I'm going to say we have x plus 7. And then on the bottom, I'm going to make a linear factor of the form x plus 3 cubed. So I'm just kind of coming up with something that we might see. So the denominator is already factored. It's linear because it's x plus 3. That part is linear, even though it's cubed. The factor form is linear. So when we break this up, it says that we have to have the sum of the following m fractions, the sum of m fractions. So the first fraction is just going to be the factor as a single term, and that factor is x plus 3. Our fractions must be proper fractions, so that means the power on the top has to be less than the power on the bottom. If this is an x, the only thing that can be smaller than an x power-wise is a number by itself. And I don't know what that number is going to be, but we're going to place an a. That a is going to represent a constant term, like a 7, a 6, a 15, a 14, a negative 3. So this will be my first partial fraction that we're making. But I have to have the sum of m fractions. So I need a second fraction. And that second fraction is going to have the x plus 3, but it's going to have the power 2. Because every power that's in that fraction needs to be represented as a partial fraction. So besides having technically this quantity to the first power, I could have that quantity to the second power. On the top of this is going to go the b variable. Because again, to keep it a proper fraction, my factor is linear, so I need something that is less as an exponent, which would just be a number. We will have one other fraction, and that other fraction is going to have the third power of that quantity cubed. Every power needs to have its own separate fraction, its own separate piece, because I can have multiple fractions with these powers that kind of create my combined fraction, and that gets us c. So anytime your factor is linear, on the top you'll just have a constant, a, b, c, and we would find that constant value. That's going to be our goal. So that is called the setup of the partial fraction, which is what part of your homework is. You're going to be just setting up the problem. So you're going to be kind of doing the breakdown step with the variables and the coefficients, the a, b, c. So that's what it looks like if it's a linear factor, meaning whatever is in parentheses is a linear form. Questions?
So on our homework, we're doing up to step number 3, like including step number 3.
We have not decomposed it yet. So this is actually considered the first step. But you have to do, like, ask yourself 1 and 2 because you have to factor it in order to get to this step. We'll work through, like, the problem so you can see what you'll be doing. Other questions? So step 4, like step 3 and step 4 usually are one or the other. So you either do step 3 or you do step 4. Sometimes they're combined, but not always. But like the first thing you ask yourself, is it a proper fraction? The second thing is factor. You have to factor in order to get them into the form. So this last one says if they're quadratic factors, so we'll say maybe 3x plus 4 on the top, and x squared plus, we'll make it a 4 again. And then I'll do this cubed again, just so you can kind of see how it separates. So it says for quadratic factors of the form ax squared plus bx plus c, so the factored term is squared, the partial fraction decomposition must include the following sum of n fractions. That n is whatever the exponent is here. So if this is cubed, you have 3 fractions. If it's squared, you have 2 fractions. If it's to the 4th, you have 4 fractions. So whatever the power is tells you how many fractions you need. So when you break it apart, each power will have its own separate fraction. So technically I would say that's the first power. I'm just going to do the denominators right now. My second power would be squared. My third power would be cubed. So whatever the outside power is would be how many fractions you should have. If that was a 6, then you'd have 6 fractions. So if this is quadratic, the factor is quadratic. Whatever is on top has to be less than the quadratic term. Well, if this is x squared, on top we can have an x term, because it's ax squared and then the bx and the c part. And I also could have a constant term, because those two pieces are less than, the powers are smaller than the x squared power. So quadratic, the terms on top could have an x, but it also could have a number by itself. So then when you move to the second fraction, once you use a letter in the alphabet, you have to do a different letter because each of these values could be different. So in my second fraction, I would have cx plus d. Magically here. What do you think is going to go on the third fraction? Ex plus f. So you need to remember your alphabet. After you use a letter, You go to the next letter in the alphabet. I mean, you could if you'd like.
So are these in any way related to the numerator?
They will be once we find them, yes. So that's what we're going to be finding. So Elena asked if they were any way related to the numerator. Yes, that's what we're going to be finding. How are they related to the numerator? So our whole goal will be to figure out how they are related to the numerator. Because they didn't update them. Like today, they never got updated. I didn't have announcements this morning. Did you have announcements this morning?
They started.
They started them late, I think. What?
We didn't because Mr. Kane wasn't.
Oh, I thought you called him Mr. Scary.
Why isn't Mr. Kane here?
Babysitter called off very last minute, and we couldn't get anybody to come this morning, so
I'm not being there messed up my teeth everywhere.
he'll be here 5th period.
Well, that's
Your
fine.
babysitter unreliable.
No, she has 106-degree fever, and I didn't want her in my house.
That's fair.
Brilliant.
But she probably knew she had a fever at like 10 a.m. But she waited until almost 9 o'clock to tell us, which at that point, like, we're stuck. So. All right.
She was just hoping she would get that.
Maybe, but like if you have a fever, the whole rule is 24 hours fever free.
Yeah.
Like I don't want her in my house because I don't want to get sick. Or I should say I don't want my kids to get sick. I care less about
Don't
myself.
hire her again.
Don't hire her again. Alright, so if you flip the page, we're gonna see if we can like actually work through.
It started. You're getting sick.
No, it's stuck. I'm not sick. It's a whole mental thing.
She's like, we just go wait it
Yeah,
out.
sick with fever.
No fever.
You're gonna come in and get all of us sick tomorrow.
And then she's gonna call off at 9 o'clock.
Yeah, no. Alright, so it says there are 4 types of problems that we're going to run into. And I know like it's weird until you start doing a problem because it's kind of hard to see what we're going to look at. So we'll either have a distinct linear, meaning the factors will be different. We'll have a repeated linear, meaning I'm going to have x plus 2 squared, that quantity squared. A distinct linear and quadratic, so one factor is linear, one factor is quadratic, or a repeated quadratic where you have quantity as quadratic and it's squared. So it says complete the first step to write the following partial fraction decomposition. First thing, is this a proper fraction?
No,
Yes.
it is.
It is a proper fraction because the power on the top is smaller than the power on the bottom. So I don't have to worry about doing any extra dividing. The top power is smaller than the bottom. The second step is to factor the denominator. You do nothing with the numerator. So how do you factor the denominator? X cubed minus x squared plus 2x minus 2.
So you take extra out of the first half and you take 2 out of the second half.
So, and that's the factor with grouping. So take, he said, an x squared out of the first half and a 2 out of the second. And then gray that becomes,
X squared plus 2 and x minus 1.
right, x squared plus 2 and x minus 1. So that's just like grouping, factor by grouping. So if I look at my denominator, I have a quadratic and a linear. So that's this third one, distinct linear and quadratic. I have both parts. Whatever your factors are become the pieces of the partial fractions that go in your denominator. So one factor is x squared plus 2. It's not to a separate power, so it just gets one fraction. The other factor is x minus 1. So each factor makes up its own fraction. What goes on the top of the quadratic factor? Because now I need to put some things up there that we're going to eventually try and find to get that numerator. So when it's quadratic, what do we have to place on top? Elena?
AX plus B.
Yeah, so ax plus b. So I need all of the values that are less than the exponent. Well, if I have an x squared, I could have an x and a number after it. The other factor is linear, it's x minus 1. So what goes on the top of that? Sean? Yeah, just a c. And again, once you use a variable or a letter in the alphabet, you're not using that anymore. So then yes, these 3 pieces would be related to that numerator, and that's going to be our goal. Can we find those values? So this is considered the first step of the partial fraction decomposition. That's what you're going to do for 51 through 56. This is the setup step. So we're going to see if we can try it again. So if you look at the example 2, it says distinct linear, and then the directions say to decompose. So we're going to actually now try and find all of the information. Is this a proper fraction?
Yes.
Yes, the power on the top is smaller than the power on the bottom. The second step would be to factor the denominator. So how does this denominator factor? Jacob?
X minus 3 is plus 2.
Yeah, so this is x minus 3, x plus 2. So I'm going to take that factor denominator and set up my fractions. It does not matter which you place first and which you have second. And that's with factoring as well. That part doesn't matter. So x minus 3 is one denominator, x plus 2 is the other. And Jacob, what goes on top of the x minus 3?
A.
And on top of the x plus 2? That doesn't get an x term with it because this is already linear. So the only thing smaller than an x is a number by itself. Questions so far? Alright, so now we're going to try and work through and solve this. So if you were working through a fraction, that's an equation. If I have a rational equation, how do you solve a rational equation? So how would I solve this? What would be the process that we would use to solve it? Alina?
Set it equal to 0.
So we could set it equal to 0. How do we try and get rid of the fractions, like the denominators? What are we trying to do to get rid of the denominators, Grant?
Well, would you find a common denominator?
We would find a common denominator and multiply the whole thing by the common denominator. So we're going to find a common denominator, and we're going to multiply this whole thing by the common denominator. So Grant, what would you say the common denominator is?
So would you just say it's that x squared minus x minus 6?
Yeah, and I'm going to use the factored form because now we have it factored. So pretty much whatever this denominator is on the left is going to be our common denominator. And we're going to multiply the whole thing by the common denominator. And that's supposed to be so on the left, we have x minus 3x plus 2, which is the common denominator. So I'm only going to have an x plus 7 because the denominator cancels. With my a term, we have an x minus 3. So Grant, the part that's missing there is
The x plus 2.
the x plus 2. So I have an a with an x and an a with a 2. And I'll place the 2 in front. I'm just distributing the a through. The x minus 3 is gone because it has the common denominator. And Grant, then the b term becomes,
Bx minus 3b.
yeah, because this needs an x minus 3. So he said it would be bx minus 3b. So you should not have fractions remaining. We multiply both the left and the right by the common denominator, which eliminates the fraction from the problem. Essentially, you're multiplying by the missing piece. What piece is it missing? That's the part that remains. So now we're going to try and group the like pieces together. So why would terms be considered like terms on the right side? Why would they be the same? Jacob? They both have an x. So we're going to look at the terms with the x, and I'm going to write them next to each other. Bless you. So ax plus bx, they're like terms because they're both containing the x. The other two pieces are also going to be like terms because they're both numbers. If it doesn't have an x, then it's a number. And I could have done this in this step, but I'm going to pull the x out just so the A and the B are together. And then here's another set. These are like terms. I'm just grouping them together to show that they're like terms. All right, so here's the part that's a little weird. Our goal is to figure out how I can get these two values on the top combined together to somehow give us the x plus 7. My x term has an a plus b with it. On the left, because this is an equation, the x term has a 1 in front of it. So if my goal is to solve for the 1 in front of the x, I'm going to take the coefficient in front of the x and place it equal to the coefficients that are with the x on the other side of the equation, because they're supposed to be equivalent. So if my x term has a 1 on the left, my x terms have to combine to be 1 on the right. The other piece is a constant term. The 7 is constant, it's just a number. That must be equal to the constant terms on the right, and those constant terms are 2a minus 3b. So we've taken the partial fractions, linking the common term from the left to the common term on the right. We're now using the coefficients because that's what we're trying to solve for. That's what A, B, C are. Those are coefficients. So we've done a ton of elimination. You can use substitution if you prefer to use substitution. Gray, what do you think you would do if we're using elimination? What would you do to try and solve for A or B? Because that's the goal. We want to find one of those levels.
You multiply it top by -2.
Sure, so if we multiply the top by -2, so now we're trying to find the A and the B in the problem. So this gives us 5, our A's cancel, and it's equal to -5B. So Gray, you now know the B is, how can you find A? Plug it back into the equation. So 1 is equal to A, and B is now -1. So Gray, that means A is equal to 2. So going back into my original problem, it said to decompose. So my final answer is to take the A and the B values and plug them into the fractions. So my fraction with A is going to be 2 over x minus 3. My fraction with B is going to be a -1 over x plus 2. Those two fractions create our original first equation. So those would be the two pieces that you would be given last year in section 8.5 when we did rational equations, that you would be asked to get a common denominator and to make that original fraction. Now we've taken that fraction and decomposed it. Questions?
How'd they figure this out? Because aren't you not supposed to split up the denominator like that and just put it in the addition sign?
Well, because of like the whole process, like no, you're not supposed to just split it up. But because we went through and used like algebraically equivalent process by eliminating the denominator and then taking like this part here, the A with the like terms, and setting it equal. So we're still using equivalency. We're creating those numbers that go on top. So no, you can't just put any two random numbers on top there. But we're finding what those numbers are by using the equivalent of the left pieces to the right pieces. So your homework tonight, 51 to 56, that's just setting it up. And then there are 5 problems, 57 through 65, where you're asked to decompose them. So you're going to have to try and work through using the common denominator, multiplying both pieces, and then like separating them. So all your problems should be very similar to this problem here. Tomorrow, obviously, we're going to go through multiple examples. Wednesday, we'll go through a couple more examples. Have an awesome day.